So our next speaker is Milica Baric and most recently Slipovich. So congratulations on that. She is receiving her master's in civil engineering from the University of Split in faculty of civil engineering and architecture. Since completing her studies, she's been working as a glass facade engineer. For the past few years, she's been employed at the University of Bundeswehr in Munich as a result, as a research assistant, and she's been investigating structural glass and the use of glass. She's been employed by Dr. Siebert and partner consulting firms as a structural engineer, and she is here today to talk about the relationship between chemical properties of different interlayers and mechanical resistance, among so many other things. So please welcome Milica.
So, hello. As already announced, our today topic is the determination of relationship between the chemical structure of different interlayers and their thermal and mechanical properties. So, what was the motivation for our work is something that actually happens pretty often in everyday engineering practice, and that's the delamination of the glass. So a lot of questions we are worried about when it comes to this topic, but some of the main ones are actually what is the reason for delamination? Is the delamination maybe a consequence of something? And could the cause maybe be found in a chemical structure? So as said, a focus of the research is actually a laminated glass. When exposed to different environmental conditions, likewise humidity or temperature changes, that has a major influence of the interlayer behavior. In general, laminated glass is a composite of the glass and the interlayer, which makes it a complex because we all know that the glass has a brittle behavior. It behaves linearly elastic until a certain point, and then without any announcement, it just breaks. That's in contrast to what happens to interlayer and how interlayer actually behaves. Not just that the interlayer doesn't have a linear behavior, it has a non-linear behavior. It's also it's a polymer, which means that the material, the model of the material is either viscoelastic or viscoplastic, which makes this whole thing even more complex. So during this research is actually just a part of our bigger research regarding the laminated glass, and this is just one part of it that we just recently did. So through this presentation, I will show you that this investigation that we did among different interlayers, which were exposed to humidity. We put a focus only on two interlayers here. Actually, we choose the most common one that has been used pretty often. It's the PVB. And also we put a huge focus on the EVA. So what we try to find is a correlation between the chemical structure and the mechanical responses of the interlayer. So for start, I will just try briefly tell you what are the main differences between these two interlayers. Actually, the PVB is both of these interlayers are polymers, and polymers are divided into different groups based on different things. But one of them is how actually their molecules are placed in order. That's how they are divided in groups. So PVB belongs to a group of amorph thermoplastics. What does that mean actually in reality? So when some polymer has a morph structure, that means that the structure of molecules are somehow in disorder, which is in a complete contrast to the composition of the EVA, which has like a combination of the order and disorder. It's actually this semi-crystalline structure. So even here on these two small pictures, you can also see how that micromolecular structures of the materials looks like. So on a picture A represents actually the amorphous thermoplastics where PVB belongs, and on the picture C is actually representation of some elastomer where EVA belongs. So that's the first difference between these two interlayers. The second big difference is actually the type of the chemical bonds which are created in between the interlayer and the glass during the lamination process. So during the lamination process of the glass and the PVB, the bonds which are created are the hydrogen bonds. And these hydrogen bonds belong to weak chemical bonds. What does that mean? That means that if in chemical equation, if we add the water, those bonds will break. What's the example of that from reality? We have laminated glass, which is somewhere outside, exposed to a higher level of humidity, or it's just a rainy day. So we have that additional water go to a chemical equation, which is actually breaking that bond, and that's actually the delamination. So that's in contrast to EVA, because EVA actually cannot react alone with the glass, which means that during the production process, certain adhesion promoters, certain sealants, so like chemical compounds, are actually added to that process, to EVA, in order to create covalent bonds. So covalent bonds belong to a strong chemical bonds. They cannot be easily broken just by adding the water to equation. We need to insert a huge amount of energy or maybe some strong acid in order to break it. So these things are like two main differences between these two interlayers. There are others, but we just don't have to go that much deep into them. So our research expectation was that to investigate whether there is a degradation of material parameters when they are exposed to a humidity experimental program. So this is the representation actually of our overall idea. What we tried to do is to whether there is a relationship, whether there is a cause and a consequence relationship between the chemical structure of a certain polymer and to thermal and mechanical properties as a consequence to something. So that the chemical structure is a cause, and maybe that actually the thermal and mechanical response is a consequence. So now I will show you the experimental program that we provided. So the first we started with this moisture absorption test. We did it for 4 weeks. So this humidity experimental program, we placed our specimens into desiccators, and every 7 days we did the infrared spectroscopy and also a tension tests. And after 28 days, after 4 weeks, we also did the differential scaling calorimetry. So in addition to that, what we also did is that before we exposed our specimens to this experimental program, we did the tension tests on both of the interlayers before they were exposed to humidity program. We also did the infrared spectrometry for it, and we also did the differential scanning calorimetry. So we had results for both of these interlayers before they were exposed to this experimental program. The reason for this was to test actually the moisture uptake when samples were exposed to a specific environment, and to investigate the influence of the structure, of the thermal properties and mechanical response. Why these three things and how actually we did that? The reason why we did the infrared spectroscopy is because to test whether there is influence on the structure, we did differential scanning calorimetry to test the thermal properties, and we did the tension test to test mechanical responses. So further for the experimental program, so as I said, the infrared spectrometry has been done before, has been done every 7 days and in the end. And in general, infrared spectroscopy is done to do the identification of the chemical structure of the polymer. This time we did it for that, but also it was important for us to see whether there are possible structural changes due to humidity exposure. It's just important to note that the infrared spectroscopy actually is measuring very thin surface layer of any kind of the material. The thickness of that is just few molecules. So maybe with that we cannot actually measure that moisture uptake, but if there are some changes on a structural level, we can see them, even though it's a pretty thin layer. Differential scanning colorimetry is used as a determination of some main characteristics of the polymer. So like to determine a glass transition of certain polymer, melting phase, crystallization phase. We did it here, but again, we did it to see whether there are some changes due to the humidity. And in the end, we also did the mechanical analysis, the tension test until breakage within the regime of the finite strains. We performed them before. Every 7 days, we presented results in a stress strain diagram, and we compared those results with those that were done before exposure to humidity program. So this is our test machine and how actually the geometry of the specimens that we used. And I'm sorry, maybe the pictures are not so good enough, but I just hope you will see what it's just important to notice here. So on the left are the EVA samples before and after exposure to humidity. It's just important to notice that they remain transparent. There's no shrinkage. And then on the right side are actually the photos of the PVB. This is actually what happened to PVB. This is something what we expected out of the experience so far, but nevertheless, just as a comparison. So this is how it actually PVB looks before and after exposure to humidity, and you can see the whitening and also the shrinkage just by being exposed to humidity program. And now let's go to our results. So here are actually the results of differential scanning colorimetry experiments, and here on the left are actually the results of the EVA interlayer before they were exposed to a humidity program, and then here are also the results of the EVA after. So on the X of both of these diagrams actually shows the temperature range that we did for this test. So it was up to -80 to up to 100 Celsius. Why we did this range? Because actually we wanted to represent and to put interlayer to go into this range that could actually really be during some exploitation process in situation in general. So it's not so uncommon that laminated glass, some kind of glass structure which is outside, or that actually temperature goes up to -20, that also temperature in a glass goes up to +40, 50. So we wanted somehow to put the interlayer into these phases, these situations that could really happen in a real life situation. And on the Y is the heat flow. And here we can also see these, what I earlier said, these three important properties of the interlayer. So the glass transition, the crystallization phase, the melting phase. And just at a glance look of these diagrams, we can see that actually there's no big difference. Actually, there is a difference. Here is just a table of the diagrams that you just seen here. So there are differences when you look at the glass transition temperature. So there are some changes, but those changes can really, not that they can be neglected, but they are pretty small. And now, when we go further with our results, so these are results of the infrared spectroscopy. So again, on the left are actually results of the EVA before it was exposed to humidity experimental program, and then on the right as the EVA after. So what we can see also on the right are actually the curves all put together. So it's the curve of the EVA before it was exposed to humidity, then for 7 days, 14 days, 21 days, 28 days. So the overlapping is not like 100%. It's not that they completely go one over another, but also the difference is not so big. So what does this diagram actually mean? That means that actually there is some water uptake with the EVA samples, but again, nothing so crucial, nothing so big. And then when we go further, or not, okay. So here are actually, oops. I'm rushing a little bit. Sorry. It just doesn't want to stop where I want to speak. Okay, finally. So here are the results. Oops, some technical help. No, it's just. Yeah, but I'm not touching anything. There. Thank you. So here are the tension test results of the EVA. So before exposure to humidity program and after. In gray are the results before. In these orangish colors are the results of the sample after. So we can see there is some degradation. But again, so this first part of the curve where material behaves linearly elastic, practically there's not a huge, not a huge influence, not a huge difference. So the model of elasticity of the material mainly remains the same. And actually, we can see some differences at the tension strength at the end. Actually, it's reduced a little bit, but when it comes to elongation and breakage, actually it remains the same. So far we can see that some correlations, some conclusions that we did based on the chemical results, on the infrared spectroscopy and on the differential scanning calorimetry, that this matches also to our mechanical results. And now here are the results of the PVB before and after. And just when we look at it, we can see that there is a difference. So again, gray results are samples before, and also the orange one are the samples after. So also in this first part of linear elastic part of the material, there's no huge influence. It's remain mainly the same. But then actually the tension strength and elongation and the breakage degradation actually happened. In general, why we are doing this research on the interlayers? So as I said at the beginning, this composite of the glass and the interlayer, the laminated glass, actually our huger and a bigger experimental program and ideas are actually to find in the end a good numerical model which could describe good not just the behavior of the laminated glass until breakage, but also what happens after breakage. And in order to do so, it's not so easy, because even in today engineering practice, when you want to choose certain interlayer, only two requirements for interlayer are there. So someone will just ask you for a tension strength, for elongation and breakage, and if it goes over it, it's okay. But it's not okay. We need to actually establish a material model which describes actually the behavior of a certain interlayer. In order to do so, we need to do all the varieties of the experiments in general. So the temperature changes, humidity test. My other colleagues are also working on it in order to establish a good material model of the interlayer, which will be used in order to establish a good model of the laminated glass in general, so that maybe in the end we can have a good numerical model of the laminated glass that we could use. So the conclusion is that we actually did the correlation of the infrared and differential scanning calorimetry and tension tests, so the combination of the chemical and mechanical tests. And as I said, this is just a part of our ongoing research that we did so far. So our ongoing research is to determine even more precise and more in details the correlation between the chemical macromolecular structure and the mechanical responses. This humidity exposure is just one of them. And so far, we can see that definitely there is a different response, different answer between EVA and PVB. So I hope you find this topic and this presentation interesting, because I also hope that soon we will be able also to publish a full paper where actually what we did, our experimental program, our results and conclusions will be presented even more in details. So thank you very much for your attention, and these are also our partners on our research project.